Proof by cases. These proofs are used when you have too many domain values to make an exhaustive proof practical. You must prove all possible cases. Most errors come from not covering all of the cases. So let's look at an example. Example being prove that if n is an integer, then n squared is an integer. In this proof, we essentially have three cases. We have case 1, where n is equal to 0. We have case 2, where n is greater than or equal to 1. And we have a third case we'll look at in a second, which is when n is less than or equal to negative 1. Essentially, this is driven by the n squared, since when you have a squared number, the inflection point is 0. What happens when it's positive? What happens when it's negative? So let's take a look at that case number 1. We've got when n is equal to 0, we have 0 squared is greater than or equal to 0. And in this case, 0 is actually equal to 0. So this is true. Then when we have the other case, case number 2 over here, when n is greater than or equal to 1, we can look at this and go, okay, well, then n squared is greater than or equal to n, simply multiplying both sides. By n, which is a valid mathematical operation, and this gives us exactly what we were trying to prove. Therefore, this case is true. Then we have case 3, where n is less than or equal to negative 1. So in this case number 3, when n is less than or equal to negative 1, that means that anytime you're going to have a value here, it's going to be a negative value. Anytime you have two negative values being multiplied together, which is your n squared, will be greater than or equal to 0. Therefore, n squared is greater than or equal to n. And this concludes the proof because we've examined each one of the three possible cases. So all cases where this where the values for this would change have been covered, and they have all three been examined to be true. For the next example, we'll show that there are no solutions in integer values for x and y for x squared plus 3y squared is equal to 8. When we have this, we have essentially the ability to combine two different kinds of proofs here. And we're going to start with a proof by cases and then go to an exhaustive. So we'll take a look at this and say, okay, well, let's just look at the x squared is greater than 8 portion of this. And we'll look at when the 3y squared greater than 8 portion of this. So when our x squared is greater than 8, only when the absolute value of x is greater than or equal to 3. And then we'll look at the 3y squared is greater than 8 when the absolute value of y is greater than or equal to 2. And we're looking at these as in terms of absolute values simply because the x is squared and the y is squared. So just looking at this, it allows us to throw out a whole bunch of potential values, everything 3 and larger for x, and everything 2 and larger for y. So this is kind of a proof by cases that allows us to narrow this down and say, okay, therefore x possible values is left with -2, -1, 0, 1, or 2. And then our y possible values are -1, 0, and 1. So then we can proceed to an exhaustive. Proof. And our exhaustive proof is now much smaller because we only have those established particular values to try out. So to start with, let's just test the largest. And see if our largest values even get us close to our number that we're targeting, which is 8. So we'll test the largest possible values. So we'll plug in our 2 or -2, doesn't matter either way because you're squaring it. So I'll just go with 2 squared plus 3 times 1 squared. And that gives us our largest possible values for x and for y is equal to 8. We'll multiply this out. We get 4 plus 3 is equal to 8. That's 7 is equal to 8. Obviously, that is false. And those were our largest values. So we can conclude and then we'll call this without loss of generality. And this is where we get that term I was talking about earlier. This is what we call WLOG, or W-log, without loss of generality type of a proof. So we conclude that without loss of generality, that other cases will fail. How can we do that? Well, we can do that because we already took a look at what happens when your x and y values exceed 3 and 2 respectively. And then we picked the largest of the remaining possible values, and those were too low. So we've tested everything lower, we've tested everything higher. So we don't have to test all the remaining values simply to prove what we already proved, because there are no other existing values possible that could get closer than the ones we tested. Therefore, without loss of generality, we can prove that there are no integer solutions x and y that satisfy this equation. Next, we'll look at this example of proof by case, but this one's going to have some errors. We're going to be missing a case, and I'm going to ask you to identify where is the error. If x is a real number, then x squared is a positive real number. And that's what we're going to prove. And we're going to say, okay, let first proposition P1 be x is positive. We'll take an example. We'll say P of 1, then Q is true. How can we say that? Well, we can say that because the product of two positives is positive. And then we'll say, all right, we'll take P, call it proposition P2, and we'll let that be x is negative. And we'll say, okay, then P of 2, then Q is true. And how is that true? Well, that's true because the product of two negative is positive. And then we would say, okay, then let's say, therefore, Q must be positive. Q being x squared is positive. Okay, therefore our theorem is true. So in this case, you went through the different possible cases. Each of the possible cases you examined was true. You're like, therefore, what our assumption was must be true. And this is one of the common errors. This looks like it would be true. However, it leaves out the possibility of, let's erase that. Case, we'll call this one P0, where x is equal to 0, resulting in x squared is equal to 0, which is our counterexample. And the one case that disproves this particular theory.